One of the first proposals in 1968 by legendary physicist and statistician Edwin Janes goes like this. Imagine you walk up to a table covered with a bunch of water flasks. The amount of water in each is roughly the same, but of course there's some slight variation. The room's temperature and pressure are pretty much the same everywhere too, but minor differences exist here as well. Now I hand you some random chemical, let's call it compound X, and ask you, what percentage of these water flasks will compound X dissolve in? Give me your best guess. If you have no prior information, Janes argued that a reasonable guess would be either 0% or 100%, or numbers very close like 1% or 99% to account for those tiny differences in the water. But Janes said guessing around 50% would feel really off, because if it were 50%, that'd mean the tiny variations between flasks were enough to flip the solubility either way. In other words, if that were true, the room's conditions would have to be perfectly balanced, right at the threshold between dissolving and not dissolving, like walking a tightrope. Unless someone's messing with you, that kind of fine-tuning would be crazy unlikely. So Janes concluded the probability chart should look like this: a high chance of 0%, an equally high chance of 100%, but a big drop in probability in between. This thought experiment gives a basic idea, but Janes went further. He proved mathematically that this had to be true. Today, he's considered one of the founders of what we now call objective Bayesianism in modern statistics. Janes never really connected this to astrobiology, but for me, the moment I heard about this thought experiment, the link was obvious. Instead of water flasks, think of possible homes for life, like star systems. And instead of asking whether compound X dissolves, we ask, does intelligent life eventually develop or not? When we look up at the stars, we wonder, what percentage of them could have intelligent life? Janes basically already gave us the answer. It's probably either close to 0% or damn near 100%, to quote Arthur C. Clarke. Both possibilities are equally terrifying. Now, a basic question you might have at this point is, how does this fit with the famous Drake equation? You know, the one that estimates the number of communicative civilizations in our galaxy as a product of 7 variables? Yeah, before you comment, I know a lot of you can't stand the Drake equation. Trust me, I get it. But honestly, I think it's become trendy to trash the Drake equation without actually listening to what Frank Drake originally meant by it. The real reason the Drake equation gets so much hate is because it's been misused. Heck, even abused. You're not supposed to just throw in random guesses for each variable, crunch the numbers, and then publish some paper claiming there are exactly 42 civilizations in the galaxy. This is way too big of a topic to cover today, but luckily I already made a 2-part video all about it, linked up here. So if we can agree, at least for now, that in theory a Drake-like equation should be possible, then it seems to clash with Janes's perspective, which argues for an all-or-nothing scenario. Here's the slick move in our new paper. We prove that these two perspectives can actually be reconciled by adding one new element to the Drake equation. Something that honestly should have been included ages ago for the whole thing to make sense. The way it stands now, the Drake equation is basically unlimited. Sure, we have some constraints on a few of the variables, but that's not really the issue. What I mean is, even before setting any constraints, you can tweak the Drake equation to spit out any crazy high number of civilizations out there. For example, let's set all the probability terms to 1. Assume civilizations last 10 billion years and say the Milky Way forms 100 stars per year. Congrats! Now you've got 1 trillion stars in our galaxy with civilizations around them. The problem is there aren't even 1 trillion stars in our galaxy to begin with. This is exactly why the standard version of the Drake equation doesn't hold up. The Drake equation has plenty of other issues too. Like, sure, it's got 7 variables, but why 7? We could easily add way more factors. Someone might reasonably say we should include the odds of multicellular life developing as a crucial step. Then someone else would argue we need to factor in the probability of language evolving, and so on and so forth. For years, I've been saying we should scrap this specific formulation and simplify it down to what I call the birth-death model. Basically, in any volume, whether we're talking about a galaxy or a supercluster, the number of civilizations has to balance out between new ones forming and old ones dying out. Each year, some civilizations emerge while others disappear. What Drake originally came up with is just a needlessly complicated version of this basic idea. Those first 6 terms, they're really just different ways to calculate the birth rate. And that last term, that's basically the inverse of the death rate. In my view, it's all these extra details that cause most of the problems and criticism people throw at the Drake equation. We'd be much better off just focusing on the core concept of birth and death rates. After enough time passes, we'd expect the number of civilizations in the galaxy to reach a steady state where new civilizations appearing each year equals the number dying out. Perfect balance. Perfectly balanced, as all things should be. The total number of civilizations appearing over time simply equals the birth rate per location multiplied by the number of available stars. Total stars minus occupied ones. Similarly, the number dying out equals the average death rate multiplied by occupied stars. When these two balance out, we reach a steady state. With some rearranging, we can express the fraction of occupied stars as this equation. Let's call this fraction F, and this term here lambda BD, the birth-to-death rate ratio. So far, we've only assumed the galaxy's civilization population is stable, not booming or collapsing. Also, while I keep saying stars, you could substitute planets or even cubic light years. The math still works. We're not specifying how civilizations arise or end either. They might emerge spontaneously or through expansion, and could fall from internal collapse or external forces. The equation holds regardless. Now let's graph F, the occupied star fraction. When the birth-to-death ratio is extremely low, few civilizations emerge, and those that do die quickly, leaving the galaxy nearly empty. As we increase this ratio, civilizations become more common until we hit diminishing returns. Eventually, nearly every star is occupied, and further increases make little difference. This S-curve should look familiar. We see it everywhere in nature, including ecosystems. Scientists have known this since at least the 1800s. Take mold growing on bread. It starts slow, spreads rapidly, then slows as it runs out of space. Just like civilizations, you can't have more mold than there is bread to grow on. Another classic example, tech adoption. Think about those early adopters rushing to buy the first-gen iPhone, followed by the mainstream crowd jumping in until growth flatlines because basically everyone who wants an iPhone already has one. Apple hits a sales ceiling. This birth-death model fixes 2 big problems with Drake's original equation. First, it's not unbounded anymore, and second, it ditches all those vague, arbitrary terms. Great. But how does this tie back to Jaynes and his all-or-nothing conclusion? The answer jumps out when we revisit this curve. Earlier, I set the x-axis range between 10 to the power of -3 and 10 to the power of 3, but realistically, these numbers could be way more extreme. Let's stretch the axis way out to reflect our uncertainty. When we do this, the middle section of the S-curve gets razor thin. Now we've got a massive range where the galaxy stays nearly empty. A massive range where it's packed full, only a microscopic sliver of scenarios where we get anything in between, in other words. This is fine-tuning, the exact link we needed to connect back to Jaynes. In our paper, we mathematically prove this. If we assume a log uniform prior for LBD, the standard we know nothing starting point for scale parameters, we show that F follows Jaynes's original distribution. Boom! We've circled all the way back to his result. Not only have we bridged the gap between Drake's and Jaynes' perspectives, we've shown they lead to the same ultimate conclusion. The galaxy is either absolutely teeming with intelligent civilizations or it's practically empty. Anything in between? That takes some serious mental gymnastics. This realization throws a wrench into the search for alien civilizations. Let's be real. The idea that nearly every star hosts a technological society seems pretty far-fetched. After decades of radio silence with no telltale signs of cosmic engineering, no Dyson swarms, no laser highways, nothing we can't explain through natural processes, the evidence, or lack thereof, speaks volumes. If civilizations were truly everywhere, we'd need Olympic-level mental contortions to explain why our telescopes show nothing but a cosmic ghost town. Earth's own history drives this point home. We've only had technology for a blink of geological time. So if we rule out the galaxy packed with aliens scenario, we're left with just two possibilities. We're in that razor-thin sweet spot of the S-curve, what Jaynes called the Valley of Improbability, or we're in the vast wasteland scenario, which frankly seems way more likely. That's why we titled both this video and our paper the way we did. Anyone hoping to detect alien signals is essentially gambling that we're in that ridiculously improbable middle ground, against all odds. When I first reached this conclusion, it hit me hard. As someone who finds SETI one of the most thrilling scientific quests out there, these results left me conflicted, even a little shaken. I grew up dreaming of hunting for alien life. Let me be crystal clear, I'm not here to claim it's a waste of time or resources, but bluntly, our research seems to point in that direction. Naturally, I've been tearing my own paper apart trying to find loopholes, which for the record is how good science works. We've got two potential escape hatches here. Two cards we could play to wiggle out of this box. Option 1. Maybe we're on that mostly empty galaxy plateau, but that doesn't mean totally empty. It just means civilizations are ultra rare. The fix. Go bigger with our searches. Current SETI efforts scan maybe 10,000 stars, but there are 100 billion more in our galaxy alone. Crank up the survey size enough and we might still hit the jackpot. The math says success requires LBD to be greater than 1 over the number of stars surveyed, but less than approximately 1. Otherwise, we'd see a crowded galaxy, which we don't. Here's the catch. Even if we scanned every star in the Milky Way, 10 to the power of 11 stars, there's no floor on how absurdly tiny LBD could be. Without a solid theory of civilization birth-death rates? For all we know, the real value could be something insane like 10 to the negative 30. In that scenario, even after scouring the entire galaxy, the odds of finding another civilization would be 10 to the negative 19, basically zero. And here's the brutal truth. There's nothing stopping LBD from being 10 to the negative 30, or even astronomically smaller. Sure, you might personally hope for better odds, but scientifically, we've got zero evidence to support that hope. Let's be honest. Belief without evidence is faith. I'm not telling anyone what to believe, but for me, accepting claims without proof is bad science. The rational approach? Stay skeptical until the evidence convinces you. Maybe we can dodge this by challenging our core assumption that galactic civilizations exist in steady-state balance between births and deaths. That's literally the only premise we're working with. If this isn't true, civilizations would either be dying out en masse or rapidly expanding. Mass extinction seems unlikely. The universe isn't getting less habitable. If anything, the early cosmos was far more dangerous, with constant gamma-ray bursts, supernovae, and chaotic star formation. An expansion phase seems more plausible. Imagine galactic empires boosting lambda BD over time through colonization. While persuasive thinkers support this, it creates its own fine-tuning problem. Even at our current spacecraft speeds, colonizing the whole Milky Way would take just a fraction of its current age. So where is everybody? At cosmic timescales, colonization waves would spread like wildfire, almost instantaneous phase transitions. This leaves us with only three possibilities. We exist before any civilization began colonizing, so there's nobody to talk to. We're living during the brief expansion phase, a cosmic blink of an eye. Or we're post-colonization, which blatantly contradicts our observations of an untouched galaxy. Try as I might, I can't escape the bleak implications of our paper. Yet there are two compelling reasons to keep searching. First, the stakes. Even with slim odds, the payoff would be revolutionary. The greatest scientific discovery in history. If we quit looking, failure becomes guaranteed. Second, maybe we're missing something. Earlier, I dismissed the empty galaxy scenario as incompatible with evidence, but that only applies to technological civilizations. Simple life could still be everywhere. We literally have zero data ruling that out. Earth's history suggests life emerges readily, and who knows? Maybe primitive organisms frequently evolve into forms of technology we can't even recognize. When we gaze at a seemingly barren galaxy, perhaps we're just looking wrong. We shouldn't just scale up searches, we need entirely new approaches. My views have evolved dramatically, as regular viewers know, and they'll keep evolving. That's how science works. We iterate, we adapt. Jane's century-old insights remind us that forgotten wisdom often holds the keys to modern problems. This mystery will haunt me forever. As curious beings, we're hardwired to scratch that insatiable itch, returning again and again, hoping one day we'll finally understand. Until next time, stay thoughtful. Stay curious. Thanks for watching. If this got you thinking, smash that like button and hit subscribe. It really helps the channel grow. Catch you next time.